welcome back. This is Dr. Oz from Western Kentucky University. So today we're going to go over an application of separation of variables to solve the population growth problem for the given country, Ukraine. So we had the data that the population of Ukraine in 2015 is 44.4 million, and the expected continuous annual rate of change, K, of the population is negative 0.006. So what that means is, since this rate is minus, so the population should decay in the long run. In part A, we're going to try to find a good model or solution to this problem in the form of exponential function. For 2015, t corresponds in this model to be t equals 5, and when we have like p of 5, that should be equal to 44.4 million. And in part B, we're going to make an estimate of the population for 2034 by using the model coming from part A, and hopefully we're going to try to see the relationship between the sign of K and the change in population for the country. So these models are generally coming out of solving a differential equation. And let me just show you what kind of differential equations would have the solution in the form of exponential growth or decay. If you have a differentiable function y of time, let's say t is time, such that y is positive and dy over dt equals, so the rate of change of y in time equals k times some constant times y, then the corresponding solution would be in the form of c e to the kt. In fact, this comes out of applying the separation of variables to this differential equation. Let me just quickly explain that to you, why we have this kind of solution here. So separation of variables says that why don't you sort of like collect all the y terms in one side of the equation and all others in the other side of the equation. So this way we can integrate both sides simultaneously, okay? And here we go. So dy over y is integrated as ln of absolute value of y. And then the right-hand side, since k is a constant, that is integrated as kt plus c. Okay, this is equivalent to say that by using the ln property, y, absolute value, is e to the kt plus c. And exponential functions are always positive, so I don't even need to carry forward the absolute value sign. And I can conclude that y equals a to the kt, but there's the c part, so I can separate e to the kt from e to the c, since c is an arbitrary constant coming out of the integration. So I can write it as like e to the c, but this is also an arbitrary constant. So why don't we call a generic arbitrary constant multiplying e to the kt to describe so like the solution, general solution of the differential equation. That's exactly where the c e to the kt comes from. As I said, c is the arbitrary constant, but in our setup, c is going to be found by the given model. And here k is the proportionality constant. So if k is positive, then we're talking about the exponential growth problem. And if k is negative, we're talking about the exponential decay problem. And speaking of the last part of the question, I was asking about the relationship between the sign of k and the growth. Obviously, if k is a negative number, so we're talking about an exponential decay problem, so we should expect the population to go down in time. All right, so we know that the solution has the form of p of t equals c e to the kt, and here p is the population in time, t is time in years, and k is the given proportionality constant or annual rate of change. So you can go ahead and write that p of t, the change of the population in years, can be represented by c times e to the minus 0.006 times t. And we want the 2015 population to happen at t equals 5. So in other words, for p equals 5, we know the population that's given in the problem as like 44.4, and that is equal to c times e to the minus 0.006 times 5. Right? So this way we're going to determine the arbitrary constant c, and that would be, in fact, let's calculate 44.4 equals c times e to the minus 0.03. So why don't we multiply both sides by e to the 0.003 so that this will cancel here. So that c, let me just write here, c would turn out to be 44.4 times e to the 0.03. And that is equal to, approximately equal to 45.75. Right? So I can go back to the model and rewrite the model here with c to be known now. It's 45.75 times e to the minus 0.006 times t. So this is sort of like the model that I'm going to use to make my estimation for future populations. All right, in part B, we're trying to estimate the population of the country in 2034. So then if we have like a time scale here, let's just think about this. So t equals 5 corresponds to 2015, and we want the population to be in 2034. So what t corresponds to 2034? So the difference between 2034 and 2015 is 2034 minus 2015, which is in fact 19. So there's 19 years in between, so this t should be 19 plus 5, which is 24. Because t is already 5 here, so if you just keep going 24 years, so you're talking about 2034 corresponding to t equals 24. All I'm going to do here is that I'm going to look for P24, which is 45.75 e to the minus 0.006 times 24. And this is approximately equal to 39.61. 39.61. All right, this tells us that if you start with the population 44.4 million in 2015, this number just tells us that if you start with the population 44.4 millions in 2015, in 19 years, the population is going to go down to 39.61 million. And that also answers part C, because the question was asking us to relate the sign of k to the rate of change. Well, since the rate is negative here, so that the population 44 million decreases all the way down to 39.61. So this is in fact the population decay problem instead of growth problem. All right, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.